So I want to take a moment to revisit the idea of roots and radicals regarding derivatives. For some reason, the author of our textbook likes to put an emphasis on roots and radicals in this implicit section. It's almost like it's a whole different idea. I'm going to do one example, and we're going to make one comment. Now, that comment is that basically when you are thinking about a root, which could be like a square root or a cube root, that's actually the same thing as a rational exponent. Now remember, rational exponent is a fraction exponent. So bottom line, a root is an exponent. And the good news is we have rules to do exponents. And we also have rules to deal with when we have like an inside and an outside part of a function. This will be a good problem. Y equals x, the square root of 2x cubed minus 2. I want to help you to see a few different things as far as navigating this problem. And honestly, that main navigation is this product. Okay, we need to see that this is going to be a product rule. It's funny, it's got a square root in it, and people get all excited about that, but it's actually that product that is more important. Now again, when it comes to the square root, we're going to interpret that as an exponent. So that means that essentially this is 2x cubed minus 2 to the 1/2 power. Of course, 1/2 power is the same thing as a square root. Okay, now we still have that product, so we're going to do the product rule. And as you start doing the product rule, you're very quickly encounter the first and then the derivative of the second. Now, the derivative of the second is a chain rule. And so when we do the chain rule, we're going to end up bringing down that exponent, subtracting from the exponent, comes out as negative 1/2, and then leave that inside alone. Okay, now we're still doing the derivative of the second, and that requires a little chain on the end of this, a 6x squared. Okay, so that's first derivative of second plus second derivative of the first, which will just come out to be recopying this 2x cubed minus 2 to the 1/2. Derivative of the first is just 1. Okay, now nothing real new here, but I do want to just focus one more time that we had a square root, we turn that into a 1/2 power, and then we see that this requires a chain rule because of course there's an inside and outside function. All ideas that we've done before. Now it turns out that this derivative needs some major simplifying. Okay, and you kind of want to be aware of this. Don't stop here. First of all, x times x squared is x cubed, and 1/2 times 6 is 3. So we have 3x cubed. Now there's a negative exponent. Of course, we've been trying to get you guys to make negative exponents we've been trying to get you to flip negative exponents. And so I flip that and write it as 1/2 power, a positive 1/2 power on the bottom. Okay, not done yet. Again, everything's good, everything's correct, but we need to be able to add these two terms together. We have a fraction term and we have a non-fraction. So what I'm getting at is that we're going to need a common denominator. Now the common denominator is, this denominator is 2x cubed minus 2 to the 1/2. Okay, but of course I have to also put a 2x cubed minus 2 to the 1/2 in the numerator. Okay, now this is very common for this kind of problem, and that is that we have these 2x cubed minus 2's with each of them having an exponent that we can add. Now when you add those exponents, you get an exponent of 1. And an exponent of 1 is pretty nice, because when I get 2x to the third minus 2 to the first power, again, I add those exponents. By the way, the common denominator stays common, it stays the same. Okay, but now that I have this exponent of 1, I'm able to basically get rid of these grouping symbols. Of course, that frees this up to be able to add some like terms and finish up with the numerator. 5x cubed minus 2 all over the common denominator of 2x cubed minus 2, still to the positive 1/2 power. Okay, this common denominator step, very common, okay, because basically we're always going to end up with a fraction and a non-fraction, which then allows me to add these exponents, again, getting an exponent of 1. Final answer, it's written with a rational exponent. It's fine. You don't need to turn it back into a square root. The funny thing is, if you turn it back into a square root, you might say that you make things a little worse, because now we have a square root in the denominator. And although a 1/2 power is the same as a square root in the denominator, we tend to just leave the answer one step before. We tend to just leave the answer as a rational exponent. In the assignment, you will see some examples that all of a sudden start throwing exponents around. That's because, or excuse me, square roots. That's because the author of our textbook wants to focus on square roots, and they happen to just kind of put it in this section. Okay, so you've got implicit, and now you've got the derivative of a square root.